Right. So good morning. Today we'll discuss digital logic design. First unit, obviously the first unit of digital logic design, that is binary systems. So in this unit we are going to cover the topics like number systems, conversions, and signed binary representation, and binary codes. So initially we'll see what is a number system. So number systems are mainly used for representing the data in different kinds of applications in different formats. For example, user or humans will be using one kind of number system, that is decimal, which we use in our daily life. When you go for a computer, it would be using something like a binary or else a hexadecimal format. So that depends upon the application which we are using. So the way of representing an operand, or the way of representing the value, is nothing but a number system. Here you can see an example which I took here, 2a, which is in hexadecimal format, and 52 in octal format. The value or the content of these two would be same, the quantity of these two would be same, but they are represented in different formats. So that depends on the application which you are using, right? And in our daily life we would be using four types of number systems, like decimal number system, binary number system, octal number system, and a hexadecimal number system. So initially we would talk about the first number system, that is decimal number system, because this is the one which we have a good knowledge in this. So decimal number system, it is also called as a base 10 system because here we are using totally 10 symbols, that is from 0 to 9, for representing any kind of value. So we are going to represent any kind of value with the help of the symbols 0 to 9. So a count is nothing but 10, so therefore the base value of this number system is 10. So that is why it is called as a base 10 system. So we'll see an example of this where I took a number, that is 5621, and have represented this in the basis of the decimal number system. Here you can see that. So here 10 is nothing but the base of the decimal number system, and this power indicates the position of this digit. So here 10 power 0 into the digit, which gives you a value, the original value. So in the same way I'm going to take the second digit, that is 2, and it gets multiplied with 10 power 1, where 1 is nothing but the position of the digit 2. So you will be getting the value as 20. Therefore I'm doing the same operation for 6 and 5, so that I will be getting the value as 5621. So this is how we are going to represent any decimal value, right? Now I'll move to the next representation, that is binary number system. So it is also called as a base 2 number system because here we use only two symbols, that is 0 and 1. So we would be using only these two symbols for representing any kind of value, and this number system is used by the computer. It will be understandable only to the computer, so the computer would be using this kind of number system, right? Now we would go to the third one, that is octal number system, which is also known as a base 8 system. So it totally uses 8 symbols. Those are 0 to 7, those are from 0 to 7. So we would be using only these symbols for representing any value, so that is why it is called as a base 8 system, right? The next one is hexadecimal number system, where it is also called as a base 16 number system. Why? Because here we are going to use totally 16 symbols, out of which the first 10 are the numericals and the remaining 6 are the alphabets. So here you can see a table where I am representing the hexadecimal representation of the decimal equivalents. You can see that 0 to 9, that is the decimal 0 to 9 will have the same representation in hexadecimal format, but when it comes to the decimal representation of 10 would be different in hexadecimal. That is here we are going to use the symbol A. So in the same way 11 is represented by using B, and so on. 15 would be represented by F. So these are what the 16 symbols which we are going to use for representing any kind of value in hexadecimal format, right? Now this is what the general form which we generally use for representing any number system. Here you can see B0, B power 0, B power 1, 2, 3, 4 and so on, and then B power minus 1, minus 2, minus 3, minus 4 and minus 5 and so on. So here this part, that is from B power 0 to B power 4, would be used for representing an integer part, and B power minus 1 to B power minus 5 would be used for representing the fractional part. So I can use this representation for representing a mixed form of number system, or a fractional number system, or an integer number system, right? So here B indicates the base, which would be 2, 8, 10 or 16, right? Now here you can see the binary scale table, where I'm going to represent some base 10 values with its equivalent binary representation along with the positional values. So the first one indicates the base value 10, that is the decimal 0 in binary would be represented with 3 zeros, and 2 power 0, the position of 0 is 0, therefore the positional value would become 1. So if you go on in the same way, the last value in the table is 111, which represents a decimal 7, and here 2 power 7 is, that is its position is 7, therefore the positional value is 128. So you are going to find out the positional value by using 2 power series, right? Now the next important concept is we have to know, we have to identify the significance in any kind of value or in any kind of number system. There are totally two significance that we identify in a given value. It is a least significant and the most significant. So the rightmost digit or symbol in any given value would be considered as a least significant digit or bit, and the leftmost digit or symbol would be considered as a most significant digit or bit. So here you can see the rightmost one is considered as a least significant digit, and the leftmost one is considered as a most significant digit. And you can take the one more example in hexadecimal, where a in this example is a least significant digit, and 1 would be the most significant digit, right? So this is mainly used in case of positional representation. So if I want to know the position, so I have to start from the least significant. If I want to know the value of this binary, then I should use the positional system, right? So I would start from the least significant bit, so that is nothing but this one. So 2 power 0, 2 power 1 and so on. Okay, so that is what the importance of knowing the significance of the bits. Next we would go to the conversions. So where do we use these conversions? See, if I take an example of a processor would be giving the output, or it would take the input in hexadecimal form, but hexadecimal form will not be understandable to the user. So if you want to understand it, you have to convert it to some other form, right? So in those cases we would be using the conversions. Now here we will be discussing how to convert a decimal value, given decimal value, into these three forms, that is binary, hexadecimal and octal, right? So in order to convert a decimal value into any other form, we would be using one algorithm. That algorithm is division algorithm. Okay, now in this I would be showing only about the integer part but not about the fractional part. So initially we will see what is that division algorithm. This method repeatedly divides a decimal number by the base of the other form and records the quotient and remainder. So here we have to divide the given decimal number with the base of the destination, and we have to preserve the remainder in each and every process. So divide the given value by the destination base, preserve the remainder, and then again divide the resultant quotient. So this process should be continued until the quotient becomes 0, right? And here the remainder digits form the equivalent LSB to MSB. The digit or the quotient, the remainder that we get from the first process would be considered as a LSB, and the remainder that we get from the last process would be considered as a MSB, right? So here we'll see an example where I'm going to convert value 25, which is in decimal format, into a binary format. So here I would consider this 25, the base of this 25 as a source, which is nothing but 10, and the base of this binary I would consider it as a destination, which is nothing but 2. So what I have to do, I have to divide the given decimal value with the destination base, right? So we'll see that. So here it is. So I'm dividing the given decimal value 25 by 2, so that I would be getting the quotient as 12 and the remainder as 1. Now this 1 in the first process would be considered as an LSB, and then I'm going to divide the resultant quotient, that is 12, again by 2. So I would be getting the quotient as 6. Now this time the balance is 0, which is nothing but the remainder, and this 6 is again divided by 2, and now I'm getting the remainder as quotient as 3 and remainder as 0. Now again this 3 is divided by 2. Now I would be getting the quotient as 1 and balance, that is remainder as 1. Now again this 1 should be divided by 2, so that I would be getting the quotient as 0 and the remainder as 1. Okay, now this is the last process, so I would be considering this as a MSB. So my value would be from LSB to the MSB. I have to write from LSB to the MSB, so it would be written as 1 0 0 1 1, or from MSB to LSB, that is 1 1 0 0 1. So this is what the exact representation of 25 in binary. Okay, so this is how we are going to convert a given decimal value into binary form. Now we would see how to convert the decimal into the octal conversion. Okay, octal form. So here I have given a decimal value which is 359. Now I want to convert this decimal value into octal form, right? So we'll see that the same method I have to use, that is division algorithm, where I'm going to divide 359 by 8. Now here the quotient is 44 and the remainder is 7. So the remainder of the first process would be considered as a LSB, and again I have to divide the resultant quotient by 8 again. So I would be getting the quotient as 5 and remainder as 4. Now again this 5 should be divided by 8, therefore the quotient would become 0 and balance, that is remainder, would become 5. Okay, so the remainder from the last process would be considered as an MSB. Therefore the value or the equivalent value of 359 in octal representation is 547. So this is how we are going to convert a given decimal into octal form. Now we would see how to convert a decimal into the hexadecimal form. Here you can see I took one example, that is 830, which is in decimal. Now I want to convert it into hexadecimal. So what I'm going to do is I'm going to divide this source, that is 830, with the base of the destination. Now the base of the destination is 16, as we have already seen that hexadecimal totally uses 16 symbols. Therefore the base of hexadecimal is 16. So 830 divided by 16, which would give you 51 as the quotient and 14 as the remainder. So how we are going to represent this 14 in hexadecimal form? Just now we have seen that we are going to represent this 14 in hexadecimal form with the help of an alphabet, that is nothing but E. Okay, now the resultant quotient should again be divided by the base of the destination, that is 16. Now this time I got the quotient as 3 and the remainder as 3. Okay, now again the resultant quotient should be divided by 16. Now this time I got the remainder quotient as 0 and remainder as 3. Therefore I have to stop the conversion process. Alright, now here the remainder of the last process would be considered as an MSB, and this would be considered, the remainder of the first process would be considered as an LSB. Therefore the value would be 33E is the hexadecimal representation of 14. Okay, now 33E is the equivalent representation of 830 in hexadecimal format. So this is how we are going to convert any given decimal to any other forms. It would be a binary, it would be a octal, or it would be a hexadecimal conversion by using a division algorithm, right? Fine. Now I'll move to the next conversion, that is binary to some other forms, where we are going to see a binary number to be converted into octal form and a binary number to be converted into hexadecimal form. So initially we'll start this conversion, that is binary to octal. Let us see that. Can be converted by grouping the binary bit in group of 3 starting from LSB. So what we have to do is we have to group 3 bits from the given binary value. 3 bits each from the given binary value. Why I'm taking 3 bits here? Why? Because 2 power 3 is nothing but 8. The maximum number of symbols that we use in octal form is 8. Therefore 2 power 3, that power should be taken, that is 3. So that is why I'm grouping 3 bits from the given binary value. Okay, let us see an example for this. Here I have given a binary number, that is 10110011. Now what I have to do is I have to group 3 bits from the LSB point of view, which is nothing but from right to left. So here, see this, have grouped, the first group is 101, there you can see here 101, and the second group is 110, and the third group is 011, and fourth group have only 2 bits. Therefore we have to append zeros in the MSB if there are less than 3 bits. Okay, appending zeros to the MSB would not be modifying the content or would not be modifying the value. So that is why I'm going to append a 0 towards the MSB, therefore it would become 010. Okay, now you totally got how many groups? 4 groups. Okay, now we have to represent these four groups in their equivalent octal form. Okay, we'll see that. So 101, the equivalent octal form of this one is 5, and then 011 is 3, and 110 is 6, and then 010 is 2. Therefore the resultant octal value is 2635. Or else here I can use the power series for calculating the equivalent values. See here, 2 power 0, 2 power 1, 2 power 2. So 2 power 0 into 1 plus 2 power 1 into 0 plus 2 power 1, so 2 power 2 into 1. There you would be getting 4 plus 0 plus 1, therefore it is nothing but a 5. So you can also go with power expansion. Okay, that is 2 power 0 to so on. Okay, so this is 2635 is the equivalent octal representation of the binary value 10110 011 101. So this is how we are going to convert a given binary number into octal form. Now let us see how to convert a given binary number into hexadecimal form. Here you can see the first point where I have shown group the bits of binary number 5 by 4 starting from the right, which is nothing but have to do the similar process which I have done for binary to octal. That is, I have to group I have grouped 3 bits in case of binary to octal, but here I have to group 4 bits. Why? Because 2 power 4 is nothing but a 16. So as I am using only 16 symbols, therefore 2 power 4, the power is nothing but 4, so I have to group only 4 bits from the LSB. Okay, replace each group of 4 bits by an equivalent hexadecimal digit, as we have done this similar way, as we have done this similar thing in case of octal, where we have represented every 3 bits by its equivalent octal. Now here we have to represent every 4 bits by its equivalent hexadecimal. So let us see an example here. Convert 10110 which is in binary into a hexadecimal number. So what I have to do here, I have to group 4 bits from the LSB towards the MSB. Okay, if there are less number of bits, that is if the bits are less than 4, then I have to append zeros in the MSB. Why? Because appending zeros in the MSB would not be modifying the content or value, right? So here you can see that. So 1010, this is one group, and then 1101, which is another group. Okay, so totally I have got two groups. Now I have to find out the equivalent representation of these groups in hexadecimal. Okay, so here 1011, which is nothing but a 11. So how we are going to represent 11 in hexadecimal? That is by using an alphabet, that is B. And 0101 is nothing but 5, so the equivalent value is B5 in hexadecimal for this binary form. So this is how we are going to convert the given binary into hexadecimal system. Okay, now let us see an exercise. So this you have to do, you have to convert this this binary value into hexadecimal as well as into octal. Okay, fine. Now we'll see the third form of conversion, that is from octal to binary or octal to hexadecimal. Okay, just now we have seen binary to octal and binary to hexadecimal. Now we would be seeing octal to binary or else octal to hexadecimal, right? So initially we'll go with octal to binary. Okay, so octal number system would be containing 8 symbols, that is it would be using only 8 symbols, that is from 0 to 7. Okay, now I have to convert it into a 2 symbol format, that is 0 and 1, right? Now what we have to do here, convert from octal to binary by converting each octal digit to a 3-bit binary equivalent. So what we have to do is we have to represent every digit of octal into a binary equivalent. So we have to represent every digit in the octal into a binary equivalent. Here you can see a table where you can see the binary equivalent of every octal digit. So 000 for 0, 001 for 1, 010 for 2, and so on, 111 for 7. So this is what the table which we have to use for converting the given octal into binary, right? So let us see an example where I took a value in octal, that is 4623. Now I have to convert this 4623 into a binary form. So what I have to do here, the thing is I have to represent each and every digit from the octal with its binary equivalent. Okay, that is 3 bits form. So here 3 would be represented by 011, and 2 would be represented by 010, and 6 would be represented by 110, and then 4 would be represented by 100. So how you are going to get this binary equivalent? Just you have to use the 2 power 0, that is power expansion, right? Now if you club all these 4 groups, then it would become a binary equivalent for the given octal number, that is 100, 110, 010 and 011. Now this is what the binary equivalent for the given octal number, that is 4623, right? Now we would see the next conversion, that is octal to hexadecimal. Okay, we'll see how to do that. Can be converted by representing each octal digit by its equivalent 3-bit binary and grouping them 4 bits from right to left. So what we have to do is we have to represent each and every octal digit in 3 bits form as we have done. Okay, but the thing is we have to group them in 4 bits form from right to left, which is nothing but LSB to MSB. Okay, similar operation that we have done for octal to binary, but the thing is here we have to group 4 bits. Okay, we have to group it 4 bits, right? So we'll see an example here. Here I have to 275, which is an octal number. Now I have to convert it into hexadecimal form. So what is the first step? I have to represent every digit of this octal into a binary form, that is in 3 bits. So 2 is represented 010, 7 would be represented by 111, and 5 would be represented by 101. Now club 3 groups, that is 101, 111 and then 010. Now what is the next step? I have to group 4 bits from right to left, by appending zeros at MSB if required. As I said, if there are less number of zeros, that is less than 4, okay, less than 4 count, then I have to append zeros, right? Now here I would be taking 1 0 1 1 from the LSB as one group, and 1 1 0 1 as the other group, and then I have only 1 0, so append zeros at the MSB, so it would become 0 0 0. So I have appended 4 zeros here. Okay, now write the equivalent representation for these bits. So 0000 is nothing but the hexadecimal representation of this one is 0, as we know that 0 to 9 in decimal is similar to the 0 to 9 representation in hexadecimal. Now 1011, which is nothing but 11, the representation of 11 in hexadecimal would be B, and 1101 is nothing but D, the representation of this value, that is 13, is D. So this is what the equivalent hexadecimal value for the given octal form, right? Now I'll go with the last conversion. Not exactly the last conversion, we have to move for see one more conversion. Okay, so hexadecimal to binary or else hexadecimal to octal.